One of the properties of liquids that we want to examine is vapor pressure. And vapor pressure is actually going to help us get into changes of state and looking at all the changes of state. But vapor pressure is a unique phenomenon in which the liquid actually changes to the gaseous state, not just at the boiling point, but at all temperatures. So in the lower left-hand corner here, we have an experiment that's designed to take a look at the vapor pressure, in this case of ethanol. And you can see that the liquid is put at the bottom of the flask. The flask was evacuated of all gases on the top. And so what it's able to do then is the liquid will then evaporate. As the liquid evaporates, the pressure goes up. Eventually it reaches a point of equilibrium. Those gas particles, as they get up to the top, they can then condense from the liquid state back down to the gaseous state. But it creates what's called then a vapor pressure equilibrium, and it happens when we get to the equilibrium between the number of molecules that are evaporating and the number that are condensing. Now, if we look up in the upper right-hand corner here, what we have is our good old kinetic energy distribution curve, or Boltzmann distribution, and we can look at the dashed line here as being the kinetic energy required for a particle that's in the liquid state to change to a gas. So a particle that's going to evaporate would have to have at least that amount of energy, and it would have to also be at the surface of the liquid in order to evaporate. So obviously the molecules that were below the surface, even if they had enough energy, they couldn't evaporate. Most of the time they would bounce into other particles and lose some of that energy. But if a particle were at the surface and had that energy, it could then evaporate and escape into the gaseous state. Mostly what would happen then is that those particles would bump into the walls of the container. They would then lose energy and then condense back down again. And so you create this equilibrium that occurs there. If we increase the temperature, so we see the distribution curve, obviously we get more molecules that have enough energy to evaporate. So our vapor pressure would then go up. As more molecules evaporated, it would increase, and you would have a greater pressure above the liquid, higher vapor pressure. If we look at different liquids, then sure enough we see that the vapor pressures, if we plot vapor pressure versus temperature, we get different curves for different substances. Meaning that the energy it takes for it to change from a liquid to a gas is different. It depends on those intermolecular forces that we're talking about. So you see something like ethylene glycol, which is used in antifreeze. It's the green line down here in the curve. Okay. All right, it has very low vapor pressures, even at high temperatures. Then you have water, ethanol, and then diethyl ether, which has very weak attraction. So it's going to have a very, very high vapor pressures. Now, these equations, like anything, these equations can be represented by equation. These lines can be represented, or curves can be represented by equations. So the Clausius-Clapeyron equation is the one that's used to describe this relationship. So we have the natural log. It turns out that taking data for these things, they found that the natural log of the pressure is equal to the negative heat of vaporization. So there's that energy relationship between going to solid, gas to liquid. Negative heat of vaporization divided by R times 1 over T plus a constant ends up giving us a relationship between that vapor pressure and the heat of vaporization and temperature. Well, if we do a kind of a look at this thing, we end up with a linear equation here. Y equals mx plus b, where this value right here is our slope. So if we do a graph of natural log of that vapor pressure versus 1 over the temperature, and of course temperature here needs to be in Kelvin, we'll get a straight line where the slope of that line is going to be equal to the negative heat of vaporization over R, And so if you take that slope, multiply it by r, and take the inverse of it, you get the heat of vaporization. So this is a real nice way to take some vapor pressure data and actually determine the heat of vaporization, or the energy it takes for something to change from liquid to gas. We're going to come back to these curves in just a minute and try to put them together with what's going on with melting solid to liquid, as well as sublimation, the solid to gas. But first, what we want to do is take a look at what boiling is. Well, we know that water boils at, or we always talk about water boiling at 100 degrees Celsius. If we look at the curve here for water, it's the blue curve, we see that at 100 degrees Celsius, there is a vapor pressure there. That vapor pressure is equal to 760 millimeters of mercury. Well, that number should sound very familiar to us. That's our standard pressure. It's 1 atmosphere. It's the pressure at sea level. That is the normal boiling point of water. Boiling will occur when the vapor pressure is equal to or greater than the atmospheric pressure. Right? So water at sea level will boil at 100 degrees Celsius because the vapor pressure at 100 degrees Celsius is 760 millimeters of mercury. If we go to, if the pressure happens to be higher than that, water is going to have to go to a higher temperature in order to boil. All right, so if we look at a pot of boiling water, if we blow up one of those bubbles and take a look at it, okay, what's inside that bubble? Well, this is where we as good science students think, all right, well, let's think about what could possibly be at the bottom of that pot of boiling water. Is there air there? No. There's no air at the bottom of the pot of boiling water. Is it empty? Well, it couldn't be empty, because if it were empty, then the pressure of the water would cause the bubble to crush in. So there's got to be something inside that bubble that's causing pressure for that bubble to exist. And the only thing in a pot of boiling water is, of course, water. So we're looking at the vapor pressure of the water causing that bubble. Well, what's on the other side of the bubble trying to push it in? Obviously, that would be the pressure of the water that's around the outside of the bubble. If we look back at our pot of boiling water here, we note that pushing down on the surface of the pot, we have air. Well, that pressure is pushing on the surface of the water. It's going to get transferred through the water. And so any bubble that forms there is going to have an interior pressure. That pressure inside the bubble is going to have to be greater than or equal to the pressure of the air in order for that bubble to form. So it's important for us to kind of understand what boiling is, and help share that with those people that don't know what boiling is, so that they understand. Now back to our vapor pressure curves. So here is what's called a phase diagram. And so our vapor pressure curve on this is the curve from point A up to point B. So that represents the transition between from liquid to gas. So the vaporization going to the right, condensation going to the left. Right, but that curve is that vapor pressure curve. Now, what we've done then is we've added data for a similar curve between the solid and liquid. That's the red line that I'm drawing now, as well as solid and gas, which is that bottom part down here. Now, one of the things you want to remember is that this graph is not truly to scale. So you have to be a little careful about how you interpret it. But the idea is that you have this one diagram here that represents all of those changes at different temperatures. So we've got temperature along the horizontal axis here, and the pressure that's being caused along the vertical axis. One of the points that we want to highlight here is the critical point. The critical point in this graph, point B, if we take another point, for instance, say point right here. Right? Well, at that temperature and that pressure, the substance would exist as a gas. It's that whole lower section there. If we increase the pressure, so we're keeping the temperature constant, right? So we're going to stay at that same temperature, but we're going to increase the pressure. Simply by increasing the pressure, we can change that gas into a liquid. If we continue to increase the pressure, we can then change it into a solid. Okay. So we don't even need to change the temperature to change something from a gas to a liquid to a solid. We can do it simply by adding pressure. Now, the significance of the critical point is at that temperature, right? So at that temperature, so that would be the critical temperature. It doesn't matter if you go above that temperature, it doesn't matter how much pressure you exert, you cannot get particles to change into a liquid or much less into a solid. The energy at that temperature is much higher than any kind of attractive force that would occur that would pull them together to become a liquid. And I guess we should also point out that the pressure that would correspond to the critical temperature, so this would be the highest temperature in which we could change it into a liquid. The pressure that would be required for that temperature would be called the critical pressure. Okay, so again, if you go to a temperature above the critical temperature, you can't possibly change a gas into a liquid. It simply has too much energy, and you wouldn't be able to change it into a liquid at that point. One of the nice things that we can use these phase diagrams for is to look at that kind of anomalous behavior of water, that it actually gets less dense when you form the solid. If you look over here on the right, it's carbon dioxide. This is our general phase diagram for most substances. And over on the left is the one for water. And if you look carefully at it, you can see that the phase change line from solid to liquid for those two are different. They're angled differently. In the water, that line angles back. So what it does is it shows you that if you are in the gaseous state, say down here, maybe that's a bad example. Let's move that over to here. If you're in the gaseous state, that you can't change it to a solid by increasing the pressure. Actually, if we do move it back over here, we can change it directly from vapor to solid. Maybe that's not a great compelling argument, but basically what it means is that as you increase the pressure, this might make more sense. If we put something here, right? If we increase the pressure from there, right? So we're in solid state. If we increase the pressure, we can actually take that substance into a liquid. So by increasing the pressure. Now this is one of the ways that they thought ice skating worked. Remember that pressure is equal to the amount of force divided by the amount of area. So we could increase the pressure on the solid ice by making a very, very small area and a lot of force. So by looking at the edge of the skates, putting all the force of your body on one edge, you could increase the pressure dramatically. So they're thinking that that was enough to actually melt the ice, to change it from solid to liquid, similar to that line that we just drew there. They since did research on it and found out that the amount of pressure, the amount of force that you would need is way more than the human could actually exert. So that ice skating is a slightly different issue, but you can see though that increasing the pressure could change the solid to a liquid. Again, increasing the pressure is going to force the particles close together, and it's going to break apart that rigid structure for ice that has those empty spaces in it. So we'll do a little bit of work with the phase diagrams in class, a little bit of analysis of these, have you guys draw some of your own, and then get ready to move on to the structure of solids.